In this lesson, we're going to look at the magnetic force on two wires carrying current when they're placed next to each other. So we have a current I1 in wire 1 straight up on the page. We have a current I2 carrying current in wire 2 straight up on the page. And we want to look at what is going to go on relative to magnetic effects and magnetic forces when these two wires interact with each other, and they do interact with each other. So let's understand that first. What's the interaction that's taking place? Well, we're going to focus first on wire 1. We're going to assume it's an infinitely long wire, and we're going to just grab our result from the last page that the B field made around wire 1 is given by mu naught I on 2 pi r. So our red current 1 makes B field around it in the shape of a circle, 2 pi r. So this is our B field here from wire 1. And when it comes around, it'll make a B field going into the paper. So you can do your IDL, right? IDL cross r hat. Right, r hat is in this direction, so IDL cross r hat, right hand rule, it's a thumb into the paper, B1 goes into the paper. Okay, well, we knew from chapter 30, or know from chapter 30, that the magnetic force is given by IL cross B, and this is where it gets to be a little tricky. And please do put in here what I have in the notes and highlight it or star it, however you want to emphasize it, that the fact that the force on wire 2, right, the force on wire 2 comes from the B field made from wire 1 and the current I and the length L2 in wire 2. So the force on wire 2 is I2 L2 cross B1. Yes, cross B1. So we have I2 L2 running straight up on the page. So this is I2 L2, and let me translate it over here. Right? So I2 L2 cross B1, and I have it drawn in here. Let me zoom in a little bit. So B1 is into the paper. My I2 L2 is straight up, and I have 90 degrees in there. That's the 90 degrees I want you to see, because that 90 degrees is my sine of 90 degrees in my cross product. And what we get is I2 L2. Oops, I2 L2. And we get our result, mu naught I1 on 2 pi r. For B1, sine of 90 degrees is 1. So here we have the force on wire 2, and we know it goes to the left when we do our cross product, IL cross B. Often, and so please make sure you get this in your notes, often in problems you're asked to solve for the force per meter on the wire. So this is the force per meter of wire, right? So please get this in, because even without knowing the length, you don't need to know the length to have the force per meter, mu naught I1, I2 on 2 pi r. And this is also really important. We do not need to calculate the force on wire 1 because we have an action-reaction pair. So what we just calculated was the force on wire 2 made by the B field from wire 1. So really it's the force on 2 by 1. Action-reaction pair is still in place. Newton's laws are laws, not suggestions. So equal in magnitude, opposite in direction. These two wires will pull together. So we would see a stress on these wires. They would pull together if they were attached at the ends. So pretty cool. And definitely you are responsible for being able to derive or calculate the force per meter or the force per unit length on a wire. Well, the only other possibilities in problems that you could be asked to solve would be, well, the exact opposite of what is here. Instead of the two currents going up, what if the two currents go down? So I want you not to solve it numerically, but just qualitatively. So take current I1 and think about what B field is it going to make at this position, and then do an IL cross B to get the force and see what direction the force points. Use your action-reaction pair to get the answer of, are they still pulling together or possibly pushing apart? And here we have the only other possibility is if the currents run in opposite directions, do the same thing. Calculate what direction the B field goes here. Now we have IDL going up to calculate the direction for the force. So if you try that, and I'll let you pause the video here and try that, I'll show you the solution when you unpause. So pause the video and give that a try. All right, hopefully you have tried that. Let's unpause and go to the next page and see what we have. Okay, so here we have B1 is out of the paper. Why is B1 out of the paper? Well, we have IDL, right? IDL, whoops, let me get red in there. IDL cross R hat. So let's do IDL cross R hat. If you right-hand rule IDL cross R hat, that is a thumb out of the paper. And now let's do IL cross B. IL cross B. Now B is coming out of the paper, so use your pen or pencil. Hold it perpendicular to the page. Use your right hand. You have to contort a little bit. IL cross B. That is going to be a thumb to the left, and then my action-reaction pair shows that they will indeed pull together, and we should have suspected that by symmetry. It doesn't matter whether the currents are going up or going down, they pull together, and here we see that if they run in opposite directions, the wires will bend apart. Well, the B1 coming out of the paper is the same because the I goes down, right? So B1 comes out of the paper, and now when we do IDL cross B, we are going to right-hand rule. That's a thumb pointing to the right, equal in magnitude, opposite in direction. Those wires will pull apart. And if you are having trouble seeing that, definitely we can talk about that in class, and we should. You need to get that straightened out. All right, the last little bit I have here at the bottom is more FYI than anything. But it is interesting because we think of electrons being the fundamental charge carriers, and electrons are fundamental, which is true. However, in terms of units, current is the fundamental unit. In other words, current was defined first. What an amp was defined first because historically it was decades after current was understood and being experimented with before the electron was discovered. The electron was discovered J.J. Thomson in around 1900. So basically the definition of current comes from looking at two very long wires, so that's why the apparatus we just talked about has historical significance. Two very long wires, 1 meter apart, carrying equal currents. The current in each wire is defined to be 1 amp when the force per length, and that's what we just talked about, that force per length is 2 times 10 to the minus 7 newtons per meter. And that may seem like an arbitrary number, but that's the number you come up with to match our SI units and our other systems of measure. So I know there's a little bit going on here, and you do definitely have to keep track of what current and what B fields are we talking about. So it will take some practice to get more comfortable doing these type problems, then we will definitely do that.